Just me.
Oh, I like very much already the very first thing you say there, that with the capital does not.
Yes,
That's very good.
well, we had a conversation.
But I mean, it's
But I
important.
read that
It's
in
really
everything.
important, though. A lot of people miss that, so that's really important to emphasize. So I'm glad you did that.
This is really small. I'm so used to a big projector and everything.
I can
So-
read it from here. Are those in the back? Can you read that?
Okay.
Yeah.
Okay.
If I would've known it was gonna be like this, I probably would've.
Maybe it's just because it's so sharp, the white on the black, but it's pretty clear. So
Okay, basically, I had to do the correlational studies. Now, it's been about 3 years since I had a stats class, so I was relearning this, had my stats book out, reading up on all this stuff, having conversations with Dr. Miller, and looking up a lot of different things to make sure I really understood what I was talking about. But this is a quantitative method that is used to determine if a relationship exists between two variables. But what's important to know is that I'm sorry, I'm being ahead of myself. You go ahead and hit the other ones. Sorry, I'm looking here. The degree to how much the variables are related is expressed as what's called the correlation coefficient, and that is represented as the letter R. And I believe that's italicized, too. Go ahead. The presence of a correlation does not indicate a cause and effect relationship, though, and oftentimes that's what happens. If you see that there's a relationship between two things, you're thinking, well, maybe this is what's causing the other thing to happen, but that's not what it is. Instead, it indicates a relationship between the variables, but not a cause and effect. And I thought that cartoon was a little relevant and to kind of lighten the mood there. Go ahead.
but wait a minute. Before you go on there,
Okay.
remember, there may in fact be a causal relationship. Correlation does not demonstrate that.
Right.
In order to demonstrate, so just because it's correlation doesn't mean that it's causation, but it also doesn't necessarily mean that there
It's not,
isn't.
Right.
So whether there is or is not correlation is just a relationship. Whether there's causality or not has to be demonstrated through other means. And you can't demonstrate causality without data that occur over time. If this, then that follows. I mean, so causation is related to if-then statements. So that requires something over time, and it also requires ruling out that there aren't other variables that are causing that, which would be the experimental data. But all of that is, you may or may not be causal. You have to demonstrate that other way. So just the fact that the correlation itself is just the relationship.
Right, and basically that was my next thing here. To determine relationship, you must use some kind of experimental
Okay, there you
method.
go. Okay. Sorry.
That's all right. That's all right. It's more convincing when it comes from you, you know? Go ahead, next one. Okay, so conducting a correlational study. I broke this down, I think, into 6 steps, which aren't listed on here, but I put a lot of the important parts from each step that you probably would really need to know. The first thing you need to do is identify 2 variables that may be related in some way, chosen based on some kind of rationale. I mean, you don't want to choose 2 things that aren't really related. For example, if you look at, well, I'm getting ahead of myself, I know it's in my PowerPoint. Go ahead. So, for example, you might look at, hit the next one, how studious a person is can be correlated with the grades they make. So how much time does a person spend on homework might be correlated with what grades they end up getting. But you've got to have something that's related in some way. You can't just choose 2 random things. So when selecting variables, you need to avoid the shotgun or fishing approach, which is when researchers select every variable that they can think of to include. You don't want to do that because you're going to eventually find a correlation by chance, possibly, and it may not be what you intended to get. Okay, so the sample size needs to be at least 30 people, and this is your unit of analysis, but you need to make sure that your unit analysis is really clear. And I do have this listed on here underneath the chart in blue. Go ahead.
But it's nice to have 30, but you can, in fact, do correlation studies with less than that.
Okay.
But it's nice to have 30, but sometimes we don't have as many of that. However, the more advanced statistical procedure, multiple regression, we can do correlation with fewer cases than you can with multiple regression. But those more advanced things that tease out various aspects of relationships, of correlational relationships that you can do with multiple regression, require bigger sample size. And it's nice to have the larger sample size with correlation, but in fact, you can get away with smaller ones.
When selecting the unit of analysis, whether you're analyzing students in a class or analyzing a classroom in school or whatever, it is really important to understand that the group you select can aggregate upward, but you can't go downwards. For example, most things in an organization, if you think about a fit into some kind of structured arrangement, if you think about where you work and how things are fit together, you might have, for example, a reading group within classes. Well, those reading groups will fit within inside a class, but that class will fit inside of a grade level, and that grade level will fit inside of a school, and that school's in a district, and the district's in the nation, so in the state, and then the state's in the nation, so forth and so on. They all fit. You can start anywhere down here, like say if you start at grade level, you can move up, but you can't move backwards. So when you're analyzing in your unit of analysis, you can't go backwards, but you can always go forward. So if at all possible, it's best to start at the lowest level, all right, of an analysis, so you can always move up. Go ahead. And I just said that, sorry. The sample should also be heterogeneous to allow for a range of scores so researchers can determine the true relationship between the variables. You want to make it sure it's as heterogeneous as possible.
Do you know what it is? Do you know what the statistical term is for data that are not heterogeneous across scores? We call it restriction of range, where the scores, and the two most common forms of restriction of range would be a floor effect or a ceiling effect. Ceiling effect is where either the test was too easy or it was taught to mastery and everybody in fact mastered it so that everybody got an A on it. Well, there's no dispersion of scores. There's restriction of range, they're all restricted to the top. Now, a floor effect would be the opposite. Either nobody studied, nobody learned, or it was too difficult, so all of the scores piled up around zero. Either way, if you correlate something with a restricted range, you're not going to get a significant correlation. Think about effort in terms of time studying for a test and a ceiling effect. Well, you may have some people that studied 2 hours, some people that studied 30 minutes, some that studied 6 hours, but that's not, how long you studied is not going to correlate with those grades if everybody got an A.
Right.
Now, if the grades are mixed from F to A, then how long they studied will probably correlate that. So that's what she's talking about there.
The third step is to select a method of measurement. Usually in correlational research, there's 2 measurements because you need one for each variable in the study. And there's several different that you could choose, obviously, based on the design and what it is that you're analyzing. The instruments that you may be using could be set up differently based on the level. They might be set up to work for a class level, or it might be a whole school-wide level type of instrument. Go ahead.
By the way, on number 3, those 2 different instruments would have to be taken by the same person.
Yes.
So whatever your group is, or whatever your set of animals are, whatever it is, whatever you're getting those measurements on, they have to come from that same person or that same unit.
Okay, so which is more reliable and accurate? And this is actually coming from something we've already talked about in class. Go ahead. From a survey, if you have a survey that's asking for respondent data, which is a person completing a survey responsible for responding for him or herself, or the informant data, where you're responding for your organization or school, which one is typically more accurate?
Informant.
The informant, and why is that?
Because you're not honing in on you're gonna, when you're a respondent and you're talking about yourself, the results may be elated. Because you're gonna say the best things you can about yourself if it's about you.
Right, typically you kind of, sugarcoat what it is that you guys say about yourself. You don't want to report anything negative about yourself. A lot of times you'll maybe avoid that part.
And by the way, that's not necessarily intentional. Much of that is unintentional. People are not aware of the fact that they're doing that.
But with the informant data, you're more likely to be honest or, more intentional in what you are saying about what's going on in your organization. Okay, go ahead.
By the way, a lot of surveys do not make that distinction about whether it's respondent or informant data. Better surveys somewhere in the introduction and the instructions will make that. That's something that you should stick into a survey if you're creating one.
Step 4 is the collect the necessary data. This needs to be collected for each variable from each participant. So if you have, say, 30% participants, you are going to collect data on your variables, whether it's 2 or 3 or however many they are, for each participant. They have to have something for each one that's there. And it has to be the same participants that you are measuring on. Go ahead. Reminder, this can be difficult for researchers conducting a prediction correlation study, which we'll talk about in a little bit, because the data needs to be collected from all participants at more than one point in time. So if you're collecting data on, say, a group of second graders right now, and you want to predict that based on a certain test score, like the Iowa test or whatever national test that they might take, that what their GPA might be when they get to, 5th grade, well, you've got to collect the data on the same set of students. But if you think about in school situations, students move, all different things happen.
Never happens in Candy's population.
No.
Especially in military. So
Yeah.
it would be really difficult sometimes to do that prediction study because you have to collect the same, get data from the same set of students or same set of participants, whoever it is in your study.
By the way, that's a threat to validity. Who's doing threats to validity? What's that one called? There's a name for that one.
Say it again, I was looking at double checking my power.
The fact that you may lose participants from 2nd grade to 5th grade on this prediction study.
Attrition.
Yes, what's it called?
Attrition.
Yes, attrition or subject mortality. Yeah, very good. So just doing cross-check to see if people are paying attention, and they were.
So here's the chart that's on your handout. For example, you could correlate, we could put more even columns on here as long as they're related in some way. You have a certain number of students, and here I'm showing a correlation between family income and students' grade level and maybe even time spent on homework nightly in minutes. And it could actually be, you can correlate these two things. Is there a correlation between this, a family's income and a student's grade? You could correlate student's grade with amount of time spent nightly. You can even correlate family income and amount of time that a student spends on homework to see if there's any kind of correlation that's done there. But it's showing you the correlation for 10 high school students is what was being used here between family income, student grades, and then of course time spent on homework. But
Are these actual data or did you just make this up?
I can't remember where I pulled some of these two, but I added that column myself. It was just to give you an example. I wanted to add something else in there to show you it doesn't have to be just 2 variables. So I wanted to put a third one that could that was related. And I tried to. There was no author on this one, so it was just something. And I was looking up information. It didn't have an author, but on some of the pictures, I put where they came from, and one of them came from this particular paper. Go ahead to the next one. The step 5 is to analyze your data, and this is using a statistical test of some sort dependent upon the variables being studied. Your variables can be continuous, and they can change according to small increments such as test scores. If it's continuous, you're going to use the Pearson method for computing the correlational coefficient, and the Pearson method is probably the most widely used one. Go ahead. Variables can be dichotomous, which means that they can be divided into categories such as gender or grades. If this was the case, then you need to convert the categories to a numerical value. Like if there's a yes or no type of response, then you assign number 1 to yes and number 2 to no or whatever. You need to assign a value to it, and then again you're going to use Pearson to analyze it. Variables can be ranked, and if they're ranked, then you're going to use the Spearman for computing the correlation coefficient.
An example of that might be to look at the rank order of teams in the National League Central for 2013, and then the rank order for those same teams in 2014, and see how much correlation there is from one year to the next. And see, because both of those whoever ended up first place, whoever ended up in fifth place, and then see how much correlation there is from one year to the next. But both of those would be a set of rank ordered data.
Let me ask this since we're on that question. Could we do that with rank order and then time spent practicing, which wouldn't be rank? Can you do,
No, the
Okay.
Spearman, both of them need to be rank order on Spearman. Now, I think that there may be, if you look up correlation in stat books, usually you'll see a chart that has like 8 different kinds of correlation coefficients. Well, a lot of people say, oh, this is so complex, I don't understand it. Really, it's not that complex. It's just that the 8 different types are for what is the level of measurement on variable A and what is the level of measurement on variable B. And as those levels of measurement change from nominal to ordinal to interval to ratio, then what is on 1 and what's on 2, there's 8 different combinations of level of measurement on variable A and level of measurement on level B. Out of all of those, most of those are not used very often. The 2 that are most common are Pearson for continuous and Spearman for rank order and rank order. The others are not used as often, and if you run into something and say, well, this one, I've got ordinal data here and I have continuous data here, what can I use? Or if I've got nominal data here and I've got continuous data here, what do I use? Look it up on that chart.
okay. Now, with dichotomy, I want to talk a bit about true dichotomy and artificial dichotomy. Which one of these two would be artificial and why? Go ahead and hit twice. Oh, no, once. Okay. Which one of these, look at what's up here. You've got a light switch that is turning a light on or off. So if the light's on, it's light, right? If the light's off, it's dark. And the other one is a dimmer switch, which does turn a light on and off too, right? But what else is there? Everything in between, right? So which one do you think is a true dichotomy where you have 2 answers, yes or no, or on, off, or light, dark?
Switch.
Or the other one would be artificial.
Switch is the true. And dimmer
Which one would be artificial?
dimmer.
The dimmer light. Because, you might say still light, dark, but you really do have that in between that you're not recognizing. So there you're turning this into an artificial dichotomy. By using something that could have in between.
The artificial dichotomy seems as if there is no continuum in between when really there is.
Right.
For example, if we simply say everything is right or wrong, well, most things there are degrees of rightness and wrongness.
Mm-hmm.
So we take something that's very complex and reduce it into the 2 simplest examples.
So it gives.
Right. So that's the true and the artificial. Correlation coefficient is measures the strength and direction of a linear relationship, and it's represented by R, and it's also called the raw coefficient. Go ahead. A perfect correlation of plus or minus 1 occurs when the data points all lie exactly on a straight line. So you've got a scatter plot. You're taking your data from this chart, have an X and Y, and you're going to plot the points and make a scatter plot. And based on the scatter plot, and then of course other equations, you're going to determine the line that runs through it. If it was all the dots landed perfectly on one line, then it's a true correlation because it's plus or minus.
No, it's not a true correlation, it's a perfect correlation.
Perfect correlation. All right, go ahead. A correlation greater than 0.8 is generally described as strong, while correlation less than 0.5 is described as weak, and that's plus or minus 0.8 or plus or minus 0.5. And I do have those listed on here as well as some examples of the scatter plots. Go ahead. A study utilizing scientific data may require a stronger correlation than a study using social science data because, go ahead, a social science will say possibly that a 0.5 is strong, and we're going to talk about that in just a second. But this is on the back of the next page. You will see the chart here, the basis of the correlations on what's a strong positive, a strong negative, and so weak and so forth in between. if you had plotted this on a scatter plot, this represents your lines. It's lines of regression, right? Is that what it's called?
Line of best fit.
Line of best fit, right, okay. So the negative would of course go down, that way the positive goes up to the right. If it's a zero correlation, it can go straight up and down or straight across. And then we also have the curve linear. For example, you could get something like this. Let's say you have an illness, and the severity of your illness is up here at the top, and here is the amount of medication you're getting. Of course, this would be reversed, all right? You would go the other way. Let's say the amount of medication you're getting based on your illness, once you get over here, your illness is getting better because you're getting more medication. But if you keep increasing the medication, it could actually go back up again because now you got side effects or overdose or whatever could happen that could take away and negate the benefit of the medication. So you could have it going the other way as well.
By the way, is it just me, or when you see medicines advertised on TV, and they have "don't take if," and for the next 2 minutes they read all these things, and you wonder who in the world would ever take that medicine? I mean, it takes them 2 minutes to read the things that could happen to you. I think, wait a minute,
Yeah,
But then they do the
am I the only one? Huh?
Disclaimer.
They do the disclaimer, your doctor will, and you will have to decide whether the risks are worth
Yeah.
taking,
Yeah, but I mean, when it takes them 2 minutes to read the list, I kind of think,
Eye drops and
I
the
don't-
side effect is your legs fall off.
Yeah,
I have
yeah.
this.
Interesting, my 11-year-old who has autism, recites those quite frequently. He'll just come off with them and he starts and I'm like.
That's cute.
And of course, this represents the scatter plots that you saw on the first page. And if you'll notice that as the numbers get closer to 1, the closer the dots get to the line. So that's another visual you can see.
you can just think of it as a vice.
Right.
And when the vice is completely closed, all of the dots have been squeezed right onto the line. It's a perfect 1-point correlation.
Right, and so the further away from the line, the less of a correlation it's going to be. So that's a visual to see how it's coming along as well. Go ahead. Okay, the next thing is the coefficient of determination.
Oh, flip back a couple times. One more. There. See where she's got her positive and negative? That's a little bit deceiving because both of those are 45-degree angles. And they don't have to be 45-degree angles. As long as it's downward sloping or upward sloping, so it doesn't have to be a perfect 45-degree angle to be a perfect 1.0. The 1.0 is whether all of the dots have been squeezed onto the line. So those are certainly examples of that, but they could be at different angles, as opposed to, it could be a 30-degree or a 15-degree angle, and it would still be perfect correlation.
Okay, the coefficient of termination determines the strength of the linear association between x and y, and is the measure of how well the regression line represents the data. It's represented by r squared, which is also called your effect size.
All right, repeat that, folks. This is really important, so talk about that a
It is
little.
on your paper. I even highlighted in blue what some things are. It denotes the strength of the linear relationship between x and y. The other one is measures the strength and direction. This one represents the actual strength, and it's gotten to by squaring your raw coefficient. Go ahead and hit it. So this represents the percent of the data that is closest to the line of best fit. All right. For example, if you have a correlation coefficient of 0.9,
Which is
then,
really high.
right, then the determination is 0.81 because you square 0.9 times 0.9 is 0.81. So that means that 81% of the total variation in y can be explained by the linear relationship between x and y, and the other 19% is not. Okay, go ahead and hit this for a second. So note that the raw coefficient of 0.5 is strong in social sciences. So in a social science type of study, that's considered strong. But what's its effect size?
0.25.
0.25. Go ahead and hit that, because 0.5 times 25 is 0.25. So then how much of it is then left unexplained?
75%.
75%. So you're saying only 25% of it is explained by this relationship. The other 75% remains unexplained. So you can see really why that correlation number should be higher.
And now stop and think about that. Humans are very complex beings. And we live in a complex society that all of the different pressures, individual pressures, societal pressures, group pressures, organizational pressures, and so it is difficult to explain 100% of what's going on. So a 0.5 correlation in the social sciences is really pretty strong. But, as you say, that leaves 75% of what's going on unexplained because it is so complex, it's difficult to capture anything that is, social sciences cannot predict exactly what an individual will do. It's impossible.
Go ahead. So the coefficient determination is a better measure than the raw correlation.
But you have to get the raw correlation to get that.
Right.
So.
Go ahead. Okay, so on your paper here, you've got a chart, and this was borrowed from our favorite book in 702, Slavin. And this was talking on correlation where it provided these studies and then what the actual correlation coefficient is. So I want you to take a second and go through and figure out what the coefficient of determination is, and you might need a calculator. And of course, I didn't write these out on mine first before I went through it.
This is really nice because it gives you different examples and you see the strength of things, of relationships that we think about all the time. That's very nicely done. By the way, for all of you who are in education, look at that very first one. If you think that what the kids bring to the home, to the school from the home doesn't make a difference. Kindergartners' fall literacy scores, is that school-based or is that home-based?
Paul? It's home
So,
based.
I mean, that just, for all of those teachers that are working with at-risk kids who don't bring that to school, look what they're up against compared to the middle-class kids that bring all of that. And yet, we're in a society that currently blames the teachers of the at-risk schools if they don't do as well as the kids in an affluent school. We currently have a society where we say there's something wrong with you as a teacher if your at-risk kids don't do as well as the kids from Scarsdale, New York. Which is kind of sad that we've gotten to that. You know, the other side of that is, it used to be that teachers weren't blamed for anything. Now we've gone 100% the opposite direction. We really need to understand teachers do make a difference, but homes make a difference too. It's not all or nothing, it's both and, like most things.
Okay, for the sake of time, let's go through, what did you get for the first one, the coefficient determination?
0.64.
0.64, then this one was
Oh, 0.23.
0.23.
0.136 or 1.14.
I put 1.4, yeah.
I put
rounded up.
0.14. Yeah.
The next one,
0.03.
0.03,
0.006.
0.006.
And 0.04.
And 0.04. So you can see that that's if you were to now turn those into percentages, which one would you think is the strongest correlation there, which of course you can see by, the correlation coefficient.
0.64.
This one right here, right?
And the top one.
And so it's, these were all studies that were done that were trying to make a correlation. But learning that there is no correlation is also just as valuable as learning that there is one. So it's, that's what I wanted to show you with that.
And by the way, even the one where time spent watching television and grades, that doesn't have much effect. However, that's probably not a very good study because it would be a better study if it were time watching television plus time playing video games. If you combine the two of those, would there be a higher effect?
Of course, that was in 1982.
Well,
so
it may, okay,
there wasn't as
Okay.
much video
Yeah.
games as there are now.
Pong.
Number 6 is to where you're going to interpret your results. When you are interpreting your results, you're going to consider both the strength and the size of the correlation coefficient. Often studies, when you are seeing a correlation study done, you will see a chart like this in there that is showing you, this is the correlation matrix, which is showing you the correlation between all of the variables used. And then it lists the correlations here. So you can see that item 1, any correlation that's going against itself is going to be a positive 1. That's why you don't see the data up there, because it's just going to repeat itself on the other side. Sometimes I've seen some that it still puts this data back up in here, but it's just a mirror of its other image. So if you're looking at item 1 and item 2, that's its correlation. Item 1 against item 3, that's its correlation, and so forth and so on. So if you were to go back and look at, the first chart we did, on one side you would have family income, students' average grade, time spent on homework, and then family income, students' grade, and time spent on homework. And you're going to look at the correlation between all of those variables. Go ahead. Sometimes, this is on your paper and it was on there too, but I forgot to mention it. A lot of times in those charts, they'll put an asterisk next to the coefficient there, and that's to indicate that it's statistically significant too. So they will put those in there as well. That chart example doesn't have any in it, but that is what that asterisk means. Go ahead. Okay, so then you're determining your statistical significance. It's a statement that the relationship between the variables at a given level of probability are truly related. And of course, this is dependent upon the sample size. If there's a
put another way, you could have a correlation of 0.3 that with an N of 30, you'd say, okay, that's significant. If you have an N of 15, you'd find it wasn't significant. It's the same strength. It's so the sample size really can have a big determination in terms of whether it is significant or not, which is one of the reasons why sometimes people look at the coefficient of determination to look at the strength of that relationship apart from whether it is significant or not, because significance is so dependent upon sample size, if that makes sense.
Mm-hmm. If there's a statistically significant effect, the null hypothesis is then rejected. A lack of significance between the two variables could be due to chance as well. So that's why you don't. That's why you can't say it's cause and effect too. Go ahead. And it's important to know that statistical significance is likely to occur if a large sample is used by researchers, regardless of whether a true relationship exists between the two variables. Because once you have so many people in there, you're bound to find some kind of relation between what it is.
If you have N equals 500, you could have a correlation of 0.15, which is not very strong, but it would certainly be significant with that large an N.
Right.
So.
Okay, there's two types of studies, and I'm going to go through this quickly because there's something I really wanted to do and I'm running out of time. One is relationship studies. Go ahead. This allows a researcher to explore the relationship between two or more variables. Go ahead. The data typically are collected at one time. It focuses on the past or the future performance of participants. And then you have your prediction studies. This is used when researchers want to predict outcomes in one variable from another variable that serves as the predictor. All right, like I talked about earlier, if you wanted to use the test score from one year and want to predict what that student's GPA might be 3 years later based on that test score. Go ahead. This involves two types of variables. You have a predictor variable and a criterion variable. The predictor variable is the variable used to predict, like the Iowa test score. All right. The criterion variable is the anticipated outcome that is being predicted, which would be GPA 3 years later. Go ahead. It's usually measured at the predictor variable is measured at one time, while the criterion variable is usually measured at a later date. And like I said earlier, that can prove difficult because of movement or whatever is going on and losing some of your sample. Single prediction studies use one predictor. Go ahead. A continuous predictor variable is used to predict a continuous criterion variable. And then here's the equation that would go with the continuous, or the single prediction study, and it has that all listed out for you on the handout. And then we have the multiple prediction study, which uses more than one predictor. A continuous predictor variable is used to predict a continuous criterion variable. And then here's the equation, but that's also called the multiple regression equation, so you might have seen that somewhere else. Okay, with multiple prediction studies, redundancy though can become an issue and researchers are faced with collinearity. What can happen is you'll get overlap sometimes. For example, go ahead. If you wanted to predict a student achievement given certain variables, your predictor criterion might be achievement, but then you're may use variables like their free and reduced lunch status, or household income, or parents' marital status, or are they recipients of state aid, or whatever. And if you look at all those different variables, there's going to be some overlap in those. And then I just listed some more advanced methods of correlation study, which I've never really even heard of, but these are the type of things that Dr. Miller was talking about earlier that, if you have this type of situation going on, you might want to look it up, or these are some more advanced ones that you can see to use for correlation that you can find in an advanced statistics class, like 601, right? Which I don't plan on
Or
doing.
maybe even beyond that on some of those.
Okay, go ahead. What I need you to do is to take out a sheet of paper and number it from 1 to 15, and I'm going to try to be as quick as possible, and I need you to put your notes up too.
Oh, that's not cool.
No notes. 1 to 15. No notes. True, false. A high degree of correlation between two variables implies that one causes the other. Number 2. The existence of a high negative correlation permits prediction. The correlation coefficient indicates the percentage of relationship between the variables. The correlation coefficient indicates the amount of common variance shared by variables. So the first one, the one before that, was it the percentage? Now this one is saying it estimates the common relationship between them. Okay, an appropriate population is one for which the data on each of the identified variables can be collected. True or false? True or false? The correlation coefficient is the best measure of a correlation. Okay. Sure, my daughter calls in the middle of presentations. The predictor variable is usually measured at one time, while the criterion variable is usually measured at a later date.
Are we on number 7?
Yes.
True or false? The predictor variable is usually measured at one time, while the criterion variable is measured at a different date. Okay? Okay, now this is a short answer. Well, fill in the blank type answer, not a sentence. This indicates that an obtained correlation coefficient is really different from a correlation of 0 or no relation, usually stated as a given level of probability. What's the word that goes there? What's that definition? Okay. This is a type of study in which a researcher identifies the variables that are correlated with the dependent variable and removes their influence so that they may not be confused with that of the independent variable. You just want me to hurry up in my quiz. That's what you're doing. All right. This is a chart on which the variables to be correlated are placed, which provides a visual representation of their relationship. This is the visual representation of the relationship. What's that chart called?
What number are we on?
10.
Okay. This is the variable that's used to predict. Which of those two variables was used to predict? All right. This is the variable that is predicted. So this is the other one. The other one was which one's used to predict, and this is the one that's predicted. All right. A dimmer switch is an example of what kind of dichotomy? Okay. What measures the percent of data closest to the line of best fit? What measures the percent of data closest to the line of best fit? What number was that? 14. Okay. Last one. What is included in a correlation matrix? Picture the correlation matrix. What's included in that? All right, run through the answers. The first one, you should put false. Go ahead and grade yourself. Go ahead. True. Go ahead. False. Then true. True again. False. True. First one answer, statistical significance. Relationship study. Scatter plot. Predictor variable, or just predictor. Okay. And the criterion variable. Artificial. Coefficient of determination. And then what's included in the matrix is all possible correlations between the variables in the study, as long as you have something similar to that. Now, if you could, look at this sheet that I put in the back of the folder. I know I'm running out of time, but I was gonna look. I was having further explanations. Look at the back of the sheet. Now, what I attempted to do with you today was a little correlation study on its own. All right? So what you're going to see here, each one of your folders had a letter on it. You are student A, B, C, D, E, or whatever. All right? What I want you to do is find you, and I want you to put where it says quiz score, I want you to put your quiz score out of 15. How many did you get right?
How do we know which one we are?
It's on your
It's on
folder,
the-
it's written on the
it's
tab
right
of your
Oh,
folder.
I'm so
Tab.
sorry. Okay, sorry.
Sorry.
The number of marks is how many you got right?
Nope. So the first one is your quiz score. The next thing I wanted you to do is look at the notes now. Take out the notes that I gave to you. I want you to count up how many times you made a mark on these notes. Not, each separate time. Did you highlight something, or did you circle something, or did you write something? Now, if you're telling about where you filled in the blank here, just use that one as one instead of this many different times. Yeah, I guess if you took notes on a sheet of paper, that counts too. But just come up with a number of how many times you made a mark on your notes.
What does that count as?
No, just each time. Not each letter, not each word. So that line is line 1, then line 2, or whatever. Each time you want to mark something down or circle something or whatever. And I want you to write the number of marks that you made in that next column. Now, since I'm running out of time, what I'm going to ask you to do is to give me your paper, and I will fill out a universal one and share it with you later to see if there's a correlation with the number of marks or notes that you took while doing this and your quiz score. See, now my timer just went off.
That's my alarm in the morning, so I'm kind of.
Please. No. And I, you know, we'll just,
I have notes on the backside.
what's that?
I have notes on the backside.
Oh, I'll give it back to you. Because you don't have to put your name on it either, because I'll just see who's letter D or whatever. Thank you.
I'm off.
I think I'll run too. I should probably put my shoes on.
I don't want to take anything that's like, not mine. I just have those two slides on there for, not sure how much time. Yep. And I had a hard time removing it the first time. It's like it. Do I have all of those, papers?
Break time now?
Yes. I am roasting.
It's hot up there, but then
Oh.
here it.
Phew. Thank you.
Careful, Gummy Bear. Not that I ever have sugar.